If you just switch partners and write it on the right side, you're making assumptions that may or may not be valid about the things interacting with each other. So we'll talk through that once we go through this definition. So we haven't gotten there yet, is my answer. Great, thank you. Can I hear from a new voice? Precipitation, what did you and your group discuss? What are some ways we can describe precipitation?
Like snow.
Okay, so what about snow?
So it starts as a liquid in the upper atmosphere, and it cools down, and it hits the cold air. So that's like the example of the reaction. It changes and forms a solid.
Okay, so I'd be a little bit careful in saying it's the chemical change, because there it's a physical change.
Yeah.
So precipitation can either be rain or snow. What's different about that? I heard a discussion up here about that as well. What makes that precipitation? What makes that similar to the chemistry definition?
It's something of less density, or of more density coming out of something of less density, like a gas or a liquid from a gas and a solid from a liquid.
So that's not necessarily density, that's phases.
Phases, okay.
So you have a liquid or a solid, right? Rain or snow in gas. There are two different phases. And what happens to the one phase? It does have somewhat to do with density. What happens to one of the two phases?
Condenses.
Separates out, right?
Separates out.
Falls to the bottom. So, kind of a combination of what you guys are talking about. So precipitation is when something goes from being in one phase, and in chemistry usually it's dissolved in the liquid, to they somehow fall out of solution, they form a solid, and that solid then usually gravity is pulling it down to the bottom. So in chemistry, why does that happen?
Solubility and insolubility.
We have all of these ions now floating around because we said that these two compounds are aqueous. So if you were to go in the magic school bus and look at the solution, you see all these ions floating around, right? And then the question you need to ask yourself is, when two of those ions bump into each other, are they going to keep going past each other or not? Each one of those ions is actually surrounded by water as well. And so they have this kind of like cloud of water around them. So you can kind of think about with water here, water here, water here. Typically about 6 water molecules surround each ion. So the question is, when a sodium ion runs into a chromate and they bump into each other, are they going to stick together or not? Why not? Yeah, how do you use the chart to decide that? That's our definition of soluble, right? Then when those two ions bump into each other, if there's a really strong attraction to each other, they're going to stop right there, and they're going to form and precipitate and fall out of solution. If they're not more strongly attracted to each other than they are attracted to the water molecules that are surrounding them, they're going to bounce off each other and keep going. That's what this table means. It's saying, if I bump into something else, am I going to stick together and fall out of solution or not? And the black squares means it's going to fall out of solution. So the reason I wanted you to write out all the ions separate is because you're going to ask yourself, if a sodium runs into, or sorry, not sodium, silver runs into nitrate, is that going to keep going or not? It's going to keep going. We know that because this is aqueous, and on the table it's a white square. If the silver runs into a sodium, is it going to keep going or not?
Yeah.
Two positively charged ions are not going to form a covalent compound, or ion compound. But then the question becomes, if silver runs into chromate, what's going to happen? How do we know that's going to stick? So if we look on our table, we're silver. It's right in the middle, Ag+. And actually, I could probably do this and show a bigger one, right? So we find where silver is, we find where chromate is, and then we find where the intersection of those two is. And we say, well, that looks like it's going to form a precipitate. So that's going to form a solid. We're not done yet, though, right? We still need to look at the other cation and say if that runs into the other anion, is that going to form a precipitate? So what are the other two that are still floating around in solution? we have sodium and not going to form a precipitate. Just because one doesn't form a precipitate doesn't mean it rules out the other one. So always check all possible combinations of ions. So that's why it's really important to write out all of your ions before you go through it. One of the ways that you're sometimes taught is just to switch the partners and then look up whether they're soluble or not. That does get you to the same place, but I think that if you logically work your way through it, it makes more sense you remember how to do that. So then we can say that yes, a precipitate will form. We can go ahead and write out that that is going to form a solid because it precipitates, it changes phases. But then these two are going to stay aqueous, which means they're really separate, but we write them as a product. Are we done?
No.
All right, go ahead and talk to your neighbors, see what else we need to do, and finish up this equation. Take about 1 minute or less.
Yeah.
So chromate is a 2 minus.
It's just not.
Oh.
Yeah, so she didn't show us the 1, 2, 3 thing. I like that. But I think aluminum is 3. Silver is 1. She didn't show us that one. I was like, okay, I like that. It's a pattern. I can remember that.
It's one of the few patterns of transition metals. Everything else, it can be multiple different states, but those three are always locked in.
It's 3, 2, 1.
Okay.
See, I didn't see that the first time. I was like, yeah, I like that. Because I could remember that. Because I was having a hard time remembering what charge zinc and silver had.
I don't know if I'm right. I'm so sorry.
All right, so what's missing? What else do we need to add to what we've written up here? We have to balance it. How do we do that? So we have 1 silver on this side, 2 on this side. How do we fix that? Let's try that, but then now we have 2 nitrates over here. So we only have 1 nitrate over here. Okay, and then let's check sodiums. We have 2 sodiums. Now we have 2 sodiums, 1 chromate, 1 chromate. All right? So that's the full process of a precipitation reaction. Could you recognize a precipitation reaction? What patterns are we going to be looking for when we have a precipitation reaction?
2 salts.
Say it nice and loud.
2 salts.
What's specific about those salts that we start with, though?
They're aqueous.
2 aqueous salts. 2 salts that are dissolved. So we have 4 ions, 4 sets of ions roaming around. And then what's the products?
A solid, a precipitate, and another aqueous.
So there will be a solid. We will have a phase change of one of them. And then usually the other one's aqueous. I think almost all the time in our classes, you're going to see aqueous and solid as your two products. Any questions? All right. Practice? Well, one of the things that might be useful, you guys are medically related, most of you. Is that true? So a couple examples that I thought were worth mentioning. Sorry, it's a lot of text. Gout and kidney stone are 2 examples of where this happens in the body. So you have, I think it's uric acid and sodium urate. That forms crystals. That's an insoluble precipitate. And that falls out in your joints. Super painful. That's gout. And then we have, same thing, in your bladder, or your kidneys. And you can get kidney stones, and that gets into your bladder. And that can also be really painful. So that's where we have 2 ions that are not more stable dissolved than they are together. So when they run into each other, if you have a high enough concentration, you're going to form those solids. And those solids are not just nice, smooth solids. They're actually really sharp crystals, and they can be extremely painful. So we kind of talked about this, the definition of solubility. Have you done labs where you get precipitates formed?
Yep.
Okay, so
But
you
not
know what the
everybody's in
visual
lab.
looks like when you pour 2 things together, and it goes from clear solution, so you get usually cloudy, and then over time that falls out of solution. So then, I think we've already talked through most of my points here. Here's a visual of what I was talking about. Solution of sodium chloride. This would be a chloride ion, and this blue one would be a sodium ion. Can you guys see all the little water molecules? Usually when you see pictures of a solution, we kind of ignore the water and say, well, it's dissolved in water. Just imagine it's there. It helps sometimes to see how the water molecules are kind of all around a salt. So you have a big salt crystal here, and that as those water molecules associate around a particular ion, the more stable that ion is, just being surrounded by water, the more likely it is to be soluble. Do you guys see any trends in the table for what ions are very stable with water surrounding them versus which ones are not? Go ahead and talk to your neighbor and try to outline which ones are more than likely found soluble and which ones are very frequently found as insoluble. And start thinking about some trends for those specific ions.
I think what it is
No, I'm
the
just talking
charges
about
always
this
balance
two,
out.
these two.
Well, look, the charges always balance out too. See, it's 1 and 1. And then like, that makes sense. Why are these solids and why are these oxygen? I don't know. I thought it was charging people out, but that's not true. Because there's some here that the charging people out and still like that one and that one. Yeah. Look, that's not what it was. Like, oh, it's color and all. That's what it is. I remember now. She's got her hand up and she's
All right, can I hear from a new voice? Looking at this table, what trends do you see in the solubility? Can I ask, you still kind of have your hand half up in the back corner with the hat on? No, you don't want to volunteer? All right. Can I get someone else to volunteer to share what you guys discussed? What trends do you see in this table?
Is it the polarity?
Go ahead. Wait, so say again? Most of... Okay, so we're kind of combining a couple different things. So you said there's a lot of soluble things. So maybe 2/3 of the table is soluble. All right, so that's good. Which ones specifically are soluble more of the time than not? Or more in more combinations than not? What trends do you see with those? Let's talk about the cations first, maybe. The positively charged ones. What trends do we have with those? Which ones are almost always soluble? The ones with lower positive charges. There are a few exceptions, right? So we have silver further on. We have... Is that the only other one? So silver has a lot of insoluble compounds that it can form. But if we have ammonium, sodium, potassium, those are almost always soluble. If you notice the ones with 3 stars, they're very interesting to form in water because they react violently with water. So it's actually really fun to see those kinds of things. All right, and so then that means by contrast, the ones with 2 or more charges are more frequently found as insoluble, or can more frequently be seen as insoluble. What about the anions, the negatively charged ones? What trends do you guys see there? Can I get a hand raised for a single voice? Sorry, I heard a couple people saying things. Go ahead. All of them? What are the trends for which ones are soluble and which ones are insoluble? Caroline? What do you mean forming an octet?
Well, the negative one charges are more dissolvable than the positive ones, and then the more negative and more positive they become, the less soluble.
Okay, so I'd be a little bit careful there because the reason that they have a negative charge or a 2- is because all the elements do have an octet. They're just holding electrons to themselves instead of sharing it in a covalent bond. So it's not about being an octet, but I think let's go back to the charge. So if we notice, there seems to be a trend with both the positive and negative ones that the larger the charges, the more likely they are to be able to form insoluble salts. Why is that? Between the negative and the positive charges. So if you have a +2 and a -2, there's going to be a stronger attraction between those when they bump into each other in solution than if you have a -1 and a +1. So yes, you can memorize this silly table. You can memorize this kind of thing that tells you what the trends are. But if you're able to think about the trends on this table, I think it becomes a lot easier. And I'm not 100% sure in this class if you guys have to memorize these for exams.
We don't.
That's good.
Yeah.
But if you're going to go into the medical field later on, it might be really useful to keep these kinds of things in mind as well. So hopefully you'll remember it more like this format than a table format of text. Right? I hate that last slide. And that's every single chem class you'll see. They'll be like, here are the rules. And I just think about trends. It's a lot easier to think about trends. All right, so let's go ahead and do some practice. We're going to have a few compounds here. I think we have them listed on the backside, question number 5. I want you to answer yes or no for each one of these. If we had these 2 ions floating around in solution, are they going to form an insoluble salt, or are they going to be soluble? The other way to say it, I guess, is the exact opposite of what I said here, right?
No.
If we put these in water, are they going to separate? Are they more stable apart or together is what we're asking. So go ahead and click in your response. Try to use the table. Talk to your neighbor. Make sure you're on the right track. Talking with Heather. Go about this. Show me how you did it.
So 2 Thursday and then 2 more likely to.
And then, can you find that exact compound on this table? Great. So both ways. All right, about 10 more seconds to make your decision. Find this one? Great.
Right. So for this one, CDCO3, CDCO3.
All right, I'm going to close out.
That was weird.
When I say closing out, it means I'm closing out. All right, majority of the class says that this is not going to dissociate. That means if you put cadmium carbonate, thank you. I need more coffee this morning. If you put that in water, is it going to separate or not? How do we determine that? So if we look, so first of all, charges, right? That's a really good first instinct. If you're on a test or you're just thinking through this in your regular life, be like, well, there's a 2+ and 2-, so it's probably going to be insoluble. You can also go back and look at your table. And if you look on your table, were you guys able to find this? Cadmium carbonate, right there. All right, so that should follow with the trends. There are exceptions, so make sure that you follow it up by checking on the table. But I agree with your guys' answers. So, yes. All right, second one. You guys can continue down the table if you finish this before I get to a full class discussion. Sodium sulfide.
Yes.
10 more seconds. Should be speeding up on these as we go. All right, that was quick. Boom. All right, why? Can we do the minus or +1 minus 2? So how do we, what could be a really quick way to answer this question? Sodium. All right, if you go back and look at that table, sodium has literally a clear column all the way down, right? Except for the ones that are reactive once they do dissolve.
Is that every one in that?
It is not every one in that column, no.
Thank you.
So it is a general trend, I think, for group 1 and 2 metals. Group 2 less so because they're 2 charged, 2 plus. I'm not 100% on these guys towards the bottom. Does anyone remember those rules off the top of your head? Yeah. So there's a number of other factors that come into play. I would actually... So you can tell I'm an organic chemist. I don't deal with metals unless I have to. So I deal with the metals that are up at the top. But you can always look this kind of stuff up. So if someone is ahead of the game right now, and you want to look up solubility of rubidium, cesium, francium, that would be awesome then to share out with the class, so then we have a better idea of that.
Okay.
All right. So let's go ahead and do the next question. Lead sulfate, lead 2 sulfate, I should say. And not quite as confident on this one. (40-4). We're saying that no, this one will not. Can we find that on the table? So lead 2 plus, almost all the way over on the right. Lead 2 plus is pretty insoluble with most things. We can go down and then find sulfate, which is about halfway down the anions. So I agree with you guys that that is not going to completely dissolve. Go ahead and write the name of this one beside it. Give you some practice with naming as well. So the verdict is group 1 insoluble. All right, closing out.
No.
Must submit answer. All right, almost a complete consensus. We're saying that yes. Why yes? What could we have done instead of spending the 30 seconds to answer that question? Positive 1 charged cation, ammonium, and the 2 group 1 metals are the only 3 columns in that are completely clear, right? The 2 sides of that. Ammonium, sodium, potassium. If you were to find the other group 1 metals, you would say the same. I'm going to assume it's always soluble. If I was sitting in your seat, I would have clicked yes, soluble, and then I would have gone and checked to make sure, because you can always change your answer, right? In this case. So I agree with you guys. And then last one. Second to last one.
That's a no. I just looked at the chart. That one's a close one.
And closing out. It's all right. I think you have to get a certain percentage of them, not all of them, for the day. What did you guys notice is weird about this one? So remember before I said that you wouldn't write 2 sodiums from sodium chromate becoming Na2 2+? But that's exactly what they wrote here for this one, right? Hg2 2+. And so that means that this salt forms whenever you form the salt with mercury, you actually have 2 mercury atoms together as part of a salt. So it's a very different cation. So if we look at that, you can see that that one is part of the black squares. If we look, it's right towards the top of it. And chloride is usually soluble, but there's a couple of exceptions, and mercury is one of those. All right, got one more for you, though. Ready? 10 seconds. Ready? Ready?
How can I disassociate it as water?
And
I'll say no.
closing out.
Yes, it is just because it's not disassociated in water.
You guys just told me the water completely dissociates in water. All right, so one of the reasons I put this in here is because in general chemistry, if you do end up taking that, we do talk about the water does to some extent dissociate in water. That the OH and the H do separate. Mind blown. Does happen. But for the most part, water is pretty stable and it stays together, and there's a stronger attraction between OH minus and H plus. So one of the things I thought you might do is say, oh, I see hydroxide is an ion, but then you have your H plus, and so that's not really, that's a covalent compound, so that doesn't really fit in with the rest of these.
Well, there was no C.
There was no C.
Yeah, this
Well,
is water.
I would answer this one no, because for the most part. All right, so that brings me to the last point of precipitation reactions. When we say it is soluble or it is not soluble, those are big categories. If you look at the very bottom of this table, see what the black square says? It says insoluble, which means that less than 0.05 molarity at room temperature. What that means is this is a sliding scale. Not every cation that's 2 plus is going to be attracted to the 2 minus anion the same strength. So some are going to dissolve a little bit more, some are going to dissolve a little bit less, but we kind of make this cutoff and say, well, if a really small amount of it dissolves, we're going to call it insoluble, but there's still going to be some of them that separate. So just keep in mind that this isn't an all or nothing, even though we call it all or nothing. All right, let's talk about what type of reactions these three are. So we're going to start talking about acid-base reactions. I want you to decide if this is an acid-base, a precipitation, or neither of those two reactions. Do 10 more seconds. Closing out. All right, how did we look at this and determine that this is a precipitation reaction? What are we looking for again? Can I hear from someone in that back corner of the room, please? What are we looking for that tells us this is a precipitation reaction? You want to volunteer since you're looking over your shoulder, man? I couldn't hear you. Okay, so this is question number 6. So for the next few, this is 6A, we'll do 6B and 6C. So you guys, if you can't see up here and you can't see on your phone, then make sure you read that paper. So can I have someone else volunteer? Can I get one of you two ladies?
You say, how did we come to that conclusion?
Yes.
I just looked at the product and it was, yeah,
So what about the products tells us that it's likely to be a precipitation reaction?
the solid and the aqueous.
Okay, so that's half of it, right? So that we have a solid and aqueous as products. What's the other component that we talked about that has to be there for a precipitation reaction? Say it nice and loud.
Yeah.
Great. All right, so if we're not talking about everything being soluble beforehand, we're not getting that precipitation, remember? We're talking about we start with all in the same phase, everything is liquid, and we change by making a solid that precipitates out. That's the way I want you to think about this. So if we have a solid over here and a solid over here, that's another type of reaction. That's not a precipitation reaction. So be careful with just looking at the products, okay? So then let's go ahead and talk about the second one. So this is 6B. Ten more seconds.
Wait, but
Yeah. So there's not that. There's nothing.
because it has no acid base and then it has no oxide salt.
So there's a little bit less certainty with this one, and it's kind of because we haven't talked about acid-base. Have you guys talked about acid-base reactions before, though? All right, we're going to spend the next 5 minutes talking about those. This is not an acid-base or a precipitation reaction. This is actually a redox reaction, and you guys will be talking about those starting next week. So let's take a look at this reaction, and I want you to talk about what's different with this one, and it might help if you read the bottom of the second worksheet Ms. Kattoum printed out for you guys.
Oh, that's acid.
So an acid-base neutralization reaction. What properties does that usually have? And does this fall into that category?
It has two aqueous that ends up with a liquid and aqueous.
What liquid specifically?
I think I had the answer right in the last one, but do the acid base things keep moving around, or is it just me? Because I thought the last one said neither was me.
No.
So when I think I got the last one wrong. Well, I had.
Does she grade by correctness?
Huh?
Does she grade by correctness? Interesting.
No. But she's very thorough.
So we're getting, she said.
She gives us a lot more time to answer the question.
Only by participation?
Okay, yay.
She can't vouch for my question.
She gives us a lot more time to answer the question. She's like, did you guys answer it, right? And we're like, yes.
They go around and tell us all, make sure we're understanding it.
Gen Chem 2 right now. And next fall, probably 14.
That you're normally taking.
Fair enough. Expectations? I don't know. All right. What are we looking for? Based off of this description, what are we looking for this reaction? How do we determine what this is? Go ahead. In the red shirt?
So, with, if it's got a hydroxide and a hydrogen, it's going to create the H2O and the salt, which is going to give you an acid-base neutralization.
Great. So a number of different properties we're looking for. Remember I said before HOH when I showed you water, and you're like, it's not going to separate because it's covalent. Well, we're going to need to look really carefully at our reactants and see if any of them have a polyatomic ion. There's a reason you have to memorize those, because it's really valuable to recognize them. You see that there's nitrate here, which is a 1- charge, and you see that there's an H there, and that's an acidic proton. So this, H+, can react with that OH-, and when they come together, they form water. But that means that you have leftovers, right? You have your calcium is left out, and your nitrate is left out, so it forms a salt. So that's kind of where this description, the overgeneralization, right, is you have OH- and H+, they come together to make water, and then you form a salt, because whatever your counter ions to the H+ and the OH- were, they're still floating around. But that salt is always going to be said, almost always, I think, said to be aqueous. So you guys have a number of problems to work through. That starts on page 2. I want you to work through these, and I want you, as you go through, to try to recognize when is there an OH- reacting with an H+. There's a little bit of text at the top there that you need to think about. as far as forming carbonate, using carbonate, and then forming carbon dioxide. So go ahead and work through problems 5 through 13. And then I want you to raise your hand and ask for Amanda, Evan, or myself to come around. If you get stuck on any one of them, try to detail what type of reaction each one of those are. And remember, it's going to be acid-base, precipitation, or neither for now. Question? Or you want me to come on? Yeah, you can do it. Go. Question?
First off, this is homework, right? It's like class ends in like 3 minutes.
So, get going.
I was just wondering.
I think.
So 5 through 13, right? Okay. So
And then look at the last 2 questions to summarize trends that you see. You're always going to have your cation. That's, what is a cation? Is that positive or negative? Correct. Correct.
Yep, it is.
Has everyone had a chance to work on question 1? Do you guys want to talk through that one real quick? So I'm going to make an executive decision that this is going to be something you turn in the beginning of next class. But what I want you to see is recognizing what type of reaction can be possible from today's class, and then practicing that. So for this reaction here, what's the initial thought? Are we expecting this to be an acid-base reaction, a precipitation?
Acid-base.
Why? What do we recognize in this that might tell us it's an acid-base?
The OH and the H.
So HCl is one of our strong acids. I think you guys might have heard of those. And then we have hydroxides. So what are our products going to be for this reaction? We know an acid base gives us water. And then we have our cation and anion left over. Is that right? Barium is a 2+ charge. We can see that from the left side. And then are we done? We have to balance our equation after we do that. So this is kind of the trend I want you guys to do. We would need a 2 in front of there and 2 waters, is that right? And that would be a balanced equation. So that's what Ms. Kattoum wants you to see. Remember, when you're writing out your salts, you're always going to have your cation, the positive charge before the negatively charged anion. You're going to want to think about what type of reaction it is first. If you don't think it's going to be a precipitation or an acid base, just write no reaction for today. There are some nuances to that you're going to see later.
How's the H2O balance with that?
So the H2O, there are 2 oxygens
And the 2 over there. Okay, got it.
and 2 hydrogens plus 2 there. Yeah. All right, so make sure to bring this and turn it in at the beginning of class on Monday. I don't need anything from you guys. Keep everything. Turn in the 2-pager and make sure to answer all the questions, including up through 15, talking about the trends that you see to recognize for those reactions. Thanks a lot, guys. Have a good weekend.